All right, here are the notes for section 9.1 sequences. So to start, defining a sequence. So sequent, set AN is a list of all numbers written in explicit order. For example, the sequence A1, A2, A3, so on and so forth. A1 is the first term, A2 is the second term, through so on and so forth. The numbers, A1, 2, 3, AN are the terms, and AN is the nth term. So example 1, should be a colon there. Find the first 6 terms and the 100th term, where AN is equal to this formula. So we need to find A1, A2, A3, A4, A5, A6, and lastly A100. We just do that by plugging the n value in for A. So if we plug 1 in, we get -1 over 2, so this is -half. If we plug 2 in, we get 1 over 5, so we get 1/5. Plug 3 in, we get -3/10. Plug 4 in, we get, well, no, that's not right, 1/10. I don't know where we got the 3 from. Plug 4 in, we get 1/17. Plug 5 in, we get -1/26. Plug 6 in, we get 1/37. And if we plug 100 in, we get 1 over 0.0001. So there's your list. So the sequence example 1 is what's referred to as explicitly because the formula for each term is defined in terms of the number of the sequence. You can also define it recursively by giving a formula for AN related to the previous terms, which we'll see in the next example. So example 2 says find the first 4 terms and the 8th term of the sequence defined recursively by the following conditions. So the first term is 4, and what this notation means down here is that each term is equal to the previous term plus 2. So the first 4 terms, so the first term is 4. Second term, I would add 2, get 6. Third term, add 2 again, get 8. Fourth term, add 2 again, and get 10. So let's see here. So if I went, so 1, 2, 3. So that'd be 12, 14, 1, 2, 3, 4, 5, 6, 7, 8. There you go. So there's your 8th term. Okay, arithmetic and geometric sequences. So an arithmetic sequence can be written in the form A plus D, A plus 2D, so on and so forth, for some constant D, which is referred to as the common difference. So it's what you're adding or technically subtracting. Works as well if D is negative. Each term in an arithmetic sequence should be obtained recursively from its preceding term by adding D. So it looks like this. So this version right here, that's the explicit version. That's the explicit because it depends only on n. Down here, it depends on the previous term. So this is the recursive, which should just say right there. All right, so example 3, for each of the following sequences, find the common difference, the 9th term, recursive model, and the explicit rule for the nth. So I'm actually not going to do those in that order. So A, the common difference, well, to get from one term to the next, I'm adding 3. So we're going to skip B because I can actually do it shorter. The recursive rule, well, each term is equal to the previous term plus 3, the common difference. D, the recursive rule, each term is equal to the first term plus n minus 1 times 3. So now if I want to go back and find the 9th term, I'm just going to plug 9 in here and plug my A1 in. Actually, I know what A1 is. I don't know why I put that there. That should just be a -5, because I know what the first term is. So for the 9th term, plug 9 in here. I get 9 minus 1 is 8. 8 times 3 is 24. -5 plus 24 is 19. So the 9th term would be 19. Okie dokie. So over here, okay, this is a bit trickier. These are natural logs. All right, so over here, the common difference is the natural log of 3. The reason this happens is that if you look at these numbers, they triple, because when you add 2 logs together, you actually multiply what's inside of them. So that, and then if I add ln3 to that, I get ln18, so on and so forth. So there's my common difference. So we're going to skip B for now. C, each term is equal to the previous term plus the natural log of 3. recursive rule be each term is equal to the first term plus n minus 1 times the natural log of 3. So if I want the ninth term, like 9, so that's going to be 8. So it's going to be 8 ln 3, which is the same thing, well, here. I was going to decide to get, so we'd have ln 2 plus 8 ln 3. Coefficients of natural logs are actually exponents. So this is the natural log of 2 times 3 to the 8th. So 2 times 3 to the, 8th. So this would be the natural log of 13122. So there you go. All right. A geometric sequence has these rules. It's a multiplier, so you have a common multiple or a common ratio. Now, if r is more than 1, the numbers will get larger. If r is less than 1, the numbers will get smaller. So here's your recursive rule. There's your explicit rule in there. So for blah, blah, common ratio, 10th term, recursive. All right, so same thing. So to find r, you take any term and divide it by the previous term. So in this case, it's -2. We'll skip b for now. So for c, the recursive rule, each term is equal to the previous term times -2. The explicit rule is the first term, which in this case is 1, times r, -2, to the n minus 1. So if I want the 10th term, that means it's going to be 1 times -2 to the 9th, which is the same thing as -2 to the 9th. So that is -512. Now you could brute force that. You could just, next term is -32, then positive 64, so on and so forth. All right, so over here, take any term and divide it by the one in front of it. So -1 minus -2, so this is 10 to the first, or just 10. If you look, 1 times 10 is 10, times 10 is 10 squared, so on and so forth. So we'll come back to B. So C, the recursive rule, previous term, times 10. Explicit rule, each term is equal to the first term times the ratio to the n minus 1. Now the reason this has to be n minus 1 is that for the first term, you want this to go away, which means it has to be the 0th power. So if I want the 9th term, this is going to be 10 to the -2 times 10 to the 8th, well, which is going to be 10 to the 6th. We'll read it in terms of exponents since we're already using exponents here. Which, if you think about it, they're just counting up. So that's 1, 2, 3, 4, 5. So the next term is going to be 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th. There's your term. Okay. So example 5, the second and fifth terms of a sequence. So first term, so second term is 6, third, fourth, fifth term is -48. Okay, so second, third, fourth, fifth. Okay, so then blah, blah, blah. Find the first term, the common ratio, and the explicit rule for the nth term. Okay, so there's something that we have to multiply by to go from one term to the next. So 6 times r, 1, 2, 3, cubed, is equal to -48. Because I took 3 steps, so I did 3 multiplication steps of r, because each step is a multiplication by the r value. So r cubed, -8. Yep. And the cube root of -8 is -2. So there's my r value. So the first term, to go backwards, instead of multiplying, you would divide. So a1 is 6 divided by -2, or -3. The common ratio we already found, so first term, common ratio, the explicit rule. So each term is equal to the first term times n minus 2, sorry, -2 to the n minus 1. If you check, if I plug 1 in, I should get my first term, -3. If I plug 2 in, I should get +6. If I plug 3, 4, 5 in, I should get -48, which all does work. Okie dokie. Graphing a sequence. Draw a graph of the sequence an with an equal blah, 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 blah. Okay. So if you're graphing a sequence, it's going to be essentially a scatter plot because n are whole numbers. So we can essentially do a t-table. So here's n, here's an, So we start 1, 2, 3, 4, we'll go up to 5 and just come up with some ordered pairs. So if n is 1, that becomes negative, that becomes 0. So the whole thing's 0. If n is 2, this becomes 1 times 1/2 or 1/2. If n is 3, it's going to be negative 2/3. If n is 4, it's going to be positive 3/4. If n is 5, it's going to be negative 4/5. And eventually you can see the pattern. You count up, top and bottom, and then flip the sign. So if you plot this, you're just going to get an ordered pair. So 1, 0, 2, 1/2, 3, negative 2/3, 4, 3/4. So it's going to bounce back and forth like this, and they're going to get closer to +1 and -1 as you go, because as these numbers get larger, they're still always going to be 1 apart, which means you're getting closer and closer to 1. All right, graph recursively. So we can do a similar thing. So n, bn. So we'll start with 1, 2, 3, 4, 5. So we know this is 4. Each term is 2 more, so 6, 8, 10, 12. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 4, 2, 6, 3, 8, 4, 10, 5, 12. So this should be a straight line had I done my points correctly. Okay, limit of a sequence. Let L be a real number. The sequence A set of AN has limit L as n approaches infinity if we can force AN to be as close to L as we wish for all sufficient large n. More formally, given any positive number epsilon, there's a positive number m such that for all n greater than some value m, we have this is less than some given value epsilon. We write the limit of the sequence equals L and say the sequence converges. Sequences that do not have limits diverge. Okay, so properties of some limits. This should be a little bit familiar. So if you add two things, so sequence AN has limit L and BN has limit M. If I add the two sequences, I add the limits. If I take the difference of the sequences, I take the difference in the limits. Multiply the limits. Multiply one of the sequences by a constant, multiply the limit by the constant. Divide them, divide the limits, assuming that the limit of the first, or BN, is not 0. So determine whether the sequence converges or diverges. If it converges, find its limit. So what I'm doing is I'm working this out. The limit as n approaches infinity of 2n minus 1 over n. So this we can rewrite as the limit as n approaches infinity of 2 minus 1 over n. Since it's a sum, I can do the limit as n approaches infinity of 2 minus the limit as n approaches infinity of 1 over n. Well, this is just 2. There's no place to plug it in. For a fraction 1 over n, as n gets very large, this fraction gets very small, essentially 0. So this would converge, and the values converge to 2. If you plot the points, eventually they will level off at y equals 2. All right, 9. Determine whether the sequences with given nth term converges or diverges. If it converges, find its limit. So let's see here. This is actually the same one we did in example 6. And if you remember the pattern, we went, what was it? N, AN. So 1, 2, 3, 4, 5. So 1 was 0, and 2 was 1/2, and then negative 2/3, and then positive 3/4, and then negative 4/5. So if you look at these values, they're bouncing back and forth. And if you remember the graph, it went up, down, up, down, up, down, up, down, up, down, up, down. So since it never settled on a value, the limit doesn't exist, which means this diverges. All right, so this one also appeared. This was example 7. So this one also diverges as well because the y values just kept growing. So they kept getting bigger and bigger. If you remember the table, we had, n, bn, so 1, 2, 3, 4, 5, so on and so forth. So this was 4, 6, 8, 10, 12. These values keep getting larger and larger, which means it never levels off at a certain value. All right, squeeze theorem. So the squeeze theorem just says that you can pinch some unknown function between the two of them. So if limit of a of n equals limit of c of n equals L, and there's some integer n for which b of n sits between a and c, then the limit of b also has to be L. So you're squeezing your third function between two. So the sequence converges and find its limit. Okay, so we know that this is true. The absolute value of the cosine of x is always less than 1, because cosine has to stay between positive 1 and negative 1. Or less than or equal to. So we can say this is true. The cosine of n over n is always less than or equal to this, which is always less than or equal to 1 over n, because cosine this is always less than 1. So we know that this has to be true. Okay. So let's see here. And if we let, so limit as n goes to infinity of negative 1 over n is 0. The limit as n goes to infinity of positive 1 over n also goes to 0, which means that since the cosine of n over n is stuck in between them, it follows that the limit as n goes to infinity of the cosine of n over n must also go to 0. So it converges. Down here you also have the absolute value theorem. Consider the sequence a of n. If the limit of the absolute value of your sequence goes to 0, then the whole limit goes to 0. Because if you do the absolute value, that takes care of something bouncing back and forth, which doesn't really matter because it doesn't matter if it goes up, down, up, down, up, down, up, down, up, down. As long as it's getting closer to 0, it's converging. And that is the end of the section.